you wouldn't mind, we can talk a little more specifically about your work with capacitance measurements. And of course, you have so many excellent publications over the years. And I know for a fact that a lot of the scientists in the industry and academia have benefited from referring to your papers. So if you wouldn't mind summarizing the work that you have done, and I know you mentioned earlier a little bit about viral vectors, etc., but I'm sure everyone would love to hear a little more about that.
Sure, I can do that. I mentioned how I got in touch initially with the technology. So we had the opportunity to work with different expression systems. There was work that we did on insect cell cultures, and already mentioned that. So baculovirus systems, what you have is a quite dramatic increase in cell size when these cells get infected. So it makes for really nice signals, which you obviously have to explain to people, because basically what will happen at a certain level of infection, your cell density will level off, but capacitance will continue to increase because of that increase in cell size. So this was basically work which was confirming what the group of Amin Kamen at the time had already been doing. We had also applied capacitance to show cell cultures, and this was done in Switzerland, where we were lucky in a way, because we're working with a system where we saw really nice changes in the signals when one specific nutrient became limiting. And then also when we added feed, we saw responses in the signal to these feed additions. And we were then able to reproduce some of these signals with a different show expression system at the National Research Council. And this is work which is still continuing right now as we speak, in combination and in collaboration also with the University of Manitoba, where they try to understand better what is actually happening at the cellular level. Can we confirm through offline measurements that intracellular conductivity is changing at certain nutrient levels, for example? So these are things I think that other groups, could still look at, because these are still areas where we have a bit of more work to do. Now, you mentioned viral vectors, and most of the work that was done after that, other than the CHO work, which is still continuing, is the work with the 293 cell line, where we're mainly looking at lentiviral vectors, but also the production, all that in process development of, for example, live influenza virus. And so these are systems where you pick up changes at the membrane level. So you will be able to explain that better, but it's capacitance per membrane area, which we think is at play. So when the virus gets out of the cell, and in particular viruses that are enveloped, such as the virus which is right now, out there and making us stay at home, coronavirus, and depending, we can talk about vaccine manufacturing later on, but capacitance should also be a tool that can be used there for that reason. Because when you look at envelope viruses, they bud out of the cell membrane. And we believe that what we see in certain systems, in particular antiviral vectors, but also to a certain extent influenza, although there are other factors at play, because influenza is very effective in killing the cells while it's produced. So there are other changes that are also occurring. But regardless, in all of these processes, what they have in common is that you get very characteristic patterns from your capacitance signal. And you can relate them back to changes in cell size or changes at the membrane level when the virus gets out. So this should not only provide you with good information when you're early in process development and you want to characterize your process, but also, for example, when you want to look at or confirm that one batch is behaving such as the previous batch, for example. So when you
like a fingerprint of a process,
batch variability, etc., reproducibility. So these are the main areas that we covered. Now, another area where we used capacitance was also in the production of viruses, but a different type of virus. And I categorize them as the non-envelope viruses. So these could be gene therapy vectors such as AAV. They could also be adenoviruses, which are still used as gene therapy vectors, but also as vaccines, and also oncolytic viruses. So in all these cases, these viruses at certain stages in the process lead to cell death. And as you explained really nicely early on, since capacitance picks that up when a cell is really dead, and when these cells basically explode because the virus gets out of the cell, you get very nice correlations of the capacitance signal with viability or cell death. And in most of these cases or processes, the harvest criterion is related back to viability. And initially this was done by Tripe and Blue, but we have good data showing that when you do that, or when you determine when to harvest through an online tool such as Capacitance, and this is a clear advantage.
So, Sven, am I right in thinking that, as you mentioned, when the viruses are released from the cell and they cause cell lysis or deaths, there is a narrow window where you should be harvesting those viruses, otherwise it impacts viral titer negatively?
Yeah, and so it might impact viral titer, and it might also impact, I'm, as you can hear, someone who has been all his professional life active in upstream processing, but also for later stages of the process itself. So for downstream processing, this might make a major difference.
I see.
Particularly when you have systems which undergo cell lysis, the longer you wait, typically, the more difficult it will be to purify the virus out.
Oh, I see. Interesting. Okay. Okay. That's excellent, Sven. Thanks for that. Really. You
There's
mentioned a little bit about vaccine production. Of course,
yes,
this is something that everyone in the world is talking about right now. So it couldn't be a more relevant time to talk about this. Um, so if you were to specifically talk about the COVID-19 situation and the vaccines that are being developed by multiple groups really across the world, uh, where do you think capacitance measurement can benefit this specific process?
so when you look at coronavirus, and obviously there are several groups now and companies working on manufacturing a vaccine, and there are different approaches. But in case that there are promising approaches which use vaccines that are produced or that will resemble the virus in a way, so this could be a virus-like particle, it could be an inactivated vaccine. So whenever you use cell culture to produce these vaccines, and chances are high that there will be at least one candidate which will manufacture it in that way, then I think one should look at capacitance as one tool to speed up process development. In particular, to look, I mean, in the first, I think the low-hanging fruit for me would be the interface of upstream and downstream processing. So determine when to harvest your bioreactor more easily than through offline sampling. Because this is also something that I wanted to bring to the discussion. The different concepts, right, that are out there. So one concept, and this is what's mostly used now in industry, offline sampling, and having several equipments with connected to the bioreactor. Some of them directly connected to the bioreactor, which is something that, when you think about GMP manufacturing, probably people will not like too much because you have plenty of sterile loops coming out of your bioreactor going directly to analyzers. And the other approach, and I've always been in favor of the alternative approach, which is using probes that will provide you with a signal from inside your bioreactor, so you don't even have to take a sample out of the bioreactor.
Yeah.
Now, probably we will never get away from sampling, but the more information we can collect directly through in situ probes, the better it will be. Yeah. So coming back to what you asked me, I don't think that capacitance is the magic bullet to resolve the COVID-19 crisis, but I think it can be a good tool to use in vaccine manufacturing and vaccine process development.
I think, Sven, to the point that you made earlier regarding offline sampling, and I agree with you that it's very difficult to completely eliminate offline sampling. But the question that really needs to be asked is, if you were to take an offline sample, when it comes to, let's say, cell density measurement, you take a sample once every 24 hours. What can you do with that information and what can you do with cell density or viable biovolume information that's taken once every 4 seconds using a capacitance probe, right? So I think this is one of the first points that you mentioned during our conversation is the question is, what does capacitance measure and what can you get out of the measurement? Like, what does it really mean to you? And I think the real difference truly is not just that it's measuring live cells and it's measuring the viable biovolume, but also that it's a real-time measurement from inside the bioreactor, so more realistic representation. That's excellent, Sven.
Aditya, real time. You're mentioning real time monitoring, and the value of having information available rapidly. One thing that has changed over the years, and again, some people might laugh at me when I say that, but it took us weeks to analyze a single run at the time, because I was as a student working alone basically.
Yes.
And it was a rather limited data set, right? Then we introduced frequency scanning, so you had you were multiplying the amount of data that you had to analyze. It took you 10 days, or whatever. It took you a week before, then it took you 10 days or 2 weeks to analyze a culture. Now, in particular, when we talk about combining capacitance with other online monitoring and real-time monitoring techniques, and specifically when we want to use these in combination for process control, I think there lies a great opportunity, because if we bring in all the smart people that are working these days on data analysis, and the buzzword is obviously artificial intelligence, but it's another way of saying that we have better tools now available to us to analyze huge data sets. And so there, I think we can still make good progress in that field.
Yeah, I think, again, excellent point there, Sven. I think this is probably a good time to finish the conversation, unless if you have anything else to add or discuss, Sven.
No, I really enjoyed that. Thank you, Aditya. This was a very good discussion.
Yeah, no, thank you, Sven. I'm sure, I think this was a fantastic discussion because it first started off by just introducing what the technology used to be so many years ago. And we talked about your initial experience and exposure to the technology. We spoke about your publications as well and the specific work that you've done. We've spoken about how the technology's evolved over the years, and we've discussed some of the challenges that are in front of the technology. And finally, we spoke about the viral vector application and the vaccine production application. So I think this is going to be quite I'm hoping it's going to be a very interesting conversation for people to listen to. So thank you once again, Sven. Thank you.
Thank you, Aditya. And I wanted to thank you for setting this up again. And I also wanted to thank in advance the editing team, because I think they'll have a bit of work to do. And obviously to everyone out there who's listening to this, stay safe.
Yeah, thank you so much, Sven.